transmission, distribution, and important aspects like safety and quality. So, let's dive into understanding how electricity travels efficiently and safely to power our daily lives. Let's take a closer look at the power generation concept. The core principle here is that a turbine converts steam energy into mechanical energy. This mechanical energy then drives a generator, which ultimately produces electrical power. The electricity generated is typically around 11 kilovolts, and it operates at a frequency of 50 Hz. Now, to understand the electrical output better, there's a fundamental formula we use. Power equals voltage times current times the square root of 3 times the power factor. This helps us calculate the real power output of the generator. For example, if we have an electrical system at 11 kV with a current of 2000 amperes and a power factor of 0.85, plugging these into the formula gives us an approximate power output of about 32 megawatts. It's also important to note that there are international standards governing these processes, including ASME PTC 22, IEC 60045, and IEEE 50. These standards ensure safety, efficiency, and consistency across power generation systems. So overall, this slide highlights the key elements of how steam turbines generate electrical power and the standards that guide this process, connecting directly to the broader theme of efficient and reliable power generation. Let's take a closer look at the step-up transformer station. Its main function is to increase the voltage from 11 kV up to between 380 and 765 kV. This step-up process is crucial because higher voltages help reduce transmission losses over long distances. The relationship between the voltages and the turns ratio in the transformer can be described by the formula V2 over V1 equals N2 over N1 essentially. This tells us that the voltage ratio is proportional to the turns ratio of the transformer. Another important point is the reduction of power losses. When we increase the voltage, the current decreases, which significantly cuts down on I²R losses. That's the resistive losses in the transmission lines. For example, if we have a 100 MW load at 11 kV, the current is about 5250 amperes. But at 380 kV, the current drops dramatically to around 150 amperes, resulting in nearly 99.7% loss reduction. Finally, it's worth noting that these transformers adhere to standards like IEC 60076 and IEEE 57, which ensure safety, reliability, and efficiency in power systems. Connecting all these points, the step-up transformer is a vital component in making our electrical transmission more efficient and cost-effective. Let's talk about transmission lines, specifically the overhead transmission line, or OHTL design. The main function here is to carry high-voltage current over hundreds of kilometers, and the key is doing this with minimal loss of energy. One important aspect to consider is the sag, which is the vertical distance between the conductor and the ground. The formula for sag is sag equals W times L squared divided by 8 times T here. W is the weight per unit length, L is the span between towers, and T is the tension in the conductor. For example, if we have a span of 400 meters, a conductor weighing 1.2 kilograms per meter, and a tension of 2,000 kilogram force, the sag would be approximately 12 meters. Now, the main components involved in an OHTL include towers, insulators, conductors, earth wires, corona rings, and dampers. Each of these plays a crucial role in ensuring the line's reliability and safety. Finally, there are standards that guide the design and construction of these lines, such as IEC 60826 and BSN 50341, which help ensure safety, efficiency, and consistency across different installations. Understanding these elements is essential as we look at how transmission lines are engineered to deliver power efficiently and reliably across vast distances. Let's take a closer look at the OHTL conductor and the materials used. The most common type is the ACSR, which stands for aluminum conductor steel reinforced. This design combines aluminum's excellent conductivity with steel's strength, making it ideal for high-tension power lines. Now, when we talk about resistance, we use the formula R equals rho times L divided by A here. R is resistance, rho is the resistivity of the material, L is the length of the conductor, and A is the cross-sectional area. This relationship helps us understand how the material properties and dimensions affect electrical resistance. For example, consider the ACSR Zebra, which has 54/7 wires and a cross-sectional area of about 428 square millimeters. Its resistance comes out to approximately 0.068 ohms per kilometer, and it can carry currents around 700 amperes. These figures highlight the balance between conductance and mechanical strength that this type of conductor provides. It's important to remember that aluminum is the main conductor material because of its good electrical conductivity and lightweight nature. Meanwhile, the steel core offers the necessary strength to support long spans and withstand environmental stresses. Finally, these conductors are manufactured according to standards such as ASTM B232 and IEC 61089, which ensure quality, safety, and performance across various applications. Connecting all these points, we see how the choice of materials and standards directly impacts the efficiency and reliability of overhead transmission lines. Let's talk about wind vibration and corona control. One of the main issues here is that wind can cause Aeolian vibration, which typically occurs in the 10 to 60 Hz range. This vibration can lead to mechanical fatigue and damage over time, so managing it is crucial for line integrity. To address this, we install Stockbridge dampers. These devices are designed to absorb the energy from the wind-induced vibrations, helping to reduce the stress on the conductors. On the electrical side, corona rings are used to distribute the electric field more evenly around the conductors and prevent corona discharge, which can cause power losses and radio interference. Now, there's a handy formula that helps us estimate the critical voltage at which corona begins to form. Vc equals 30 times the radius r, times the logarithm of the ratio d over r, multiplied by the square root of the conductor's tension delta. Mathematically, it's written as Vc equals 30 r log, d over r times the square root of delta. For example, if we consider a 400 kV line with a conductor radius of 1.5 centimeters and a spacing d of 300 centimeters, plugging these into the formula gives us a critical voltage, Vc, of approximately 365 kilovolts. This helps us ensure that our operating voltage stays below this threshold to prevent corona. Lastly, it's important to remember that these practices are guided by standards like IEC 60815, which provides comprehensive guidelines for the design and performance of these corona control measures. Overall, implementing these solutions effectively enhances the reliability and efficiency of our transmission lines. Let's talk about the step-down substation and distribution process. Here, the voltage is gradually reduced through a series of steps. We start from high voltages like 765 kilovolts, then step down to 400, 220, 132, 33, and 11 kilovolts, finally reaching a standard of 220 volts for use in homes and businesses. This gradual reduction is crucial for efficient power transmission and safety. Now, to understand how well these transformers perform, we use a simple formula for efficiency, which is the ratio of output power to input power, multiplied by 100 to get a percentage. So, eta equals Pout divided by Pin times 100. For example, if we have a 100 kVA transformer that incurs losses of about 1.5 kilowatts, its efficiency would be approximately 98.5%. That's pretty high, indicating most of the power is transmitted effectively with minimal losses. Finally, it's important to note that these transformers and systems are governed by international standards like IEC 62271 and IEEE 141. These standards ensure safety, reliability, and consistency across different equipment and applications. All these points highlight how crucial proper voltage step-down and efficiency management are in delivering reliable electrical power from generation to end user. Let's take a closer look at the key steps involved in ensuring construction, safety, and quality for our project. First, we start with a comprehensive survey and soil investigation. This step is crucial because it helps us understand the ground conditions and design a foundation that is both safe and durable. Next is the foundation casting, where we use M20 concrete to create a solid base. For example, in the case of a SEC 380 kV tower, the foundation measures 4 by 4 meters and is approximately 2.5 meters deep. Following that, we move on to tower erection and bolting, which involves carefully assembling the structure and securing all components properly. Then comes conductor stringing and sag measurement, ensuring the conductors are correctly installed and have the right tension for optimal performance. After that, we perform earthing and resistance testing, aiming for resistance values below 5 ohms to guarantee safety and proper grounding. Finally, we conduct a thorough final inspection before commissioning the system, making sure everything meets our safety and quality standards. Throughout this process, we adhere to important codes like IEC 61936, NFPA 70E, and ISO 9001, which guide us in maintaining high safety and quality standards. All these steps are essential to deliver a reliable and safe power transmission infrastructure. Let's talk about domestic utilization and protection. The standard voltage for household systems is typically 220 volts for single-phase and 400 volts for three-phase setups. When calculating power, we use the simple formula P equals V times I, where P is power, V is voltage, and I is current. For example, a 1.5-ton air conditioner typically consumes about 2.2 kilowatts. This means that, for such an AC, the current draw at 220 volts is approximately 10 amps. Protection devices are crucial to ensure safety and proper operation. These include miniature circuit breakers, or MCBs, residual current devices, or RCDs, proper earthing with resistance less than or equal to 1 ohm, and surge protectors to guard against voltage spikes. It's also important to adhere to certain standards, like IEC 60364, which covers electrical installations, and ISO 9001, ensuring quality management. These standards help us maintain safety, reliability, and efficiency in our electrical systems. Connecting all these points, proper utilization and protection are fundamental to safe domestic electrical systems, aligning with our overall goal of safe and efficient electrical practices at home.